Welcome everyone. My name is Mika Dementiev. I work for Nokia, where I'm a project manager in airframe R&D. I'm based in Espoo, Finland. Along with me here is Mikko Suni, a solution architect from Intel, also based in Espoo, Finland. Today we are going to talk about one new OCP Open Edge server solution with off-the-shelf accelerator for virtual RAN. Here you can see us and our email addresses in case you have some questions related to the topics or products presented here. So I'm Mika Dementiev and the other presenter is Mikko Suni. The presentation today is to introduce the One U Open Edge server solution capabilities for telecom far edge deployments. As an example, we show case study for vRAN where Intel off-the-shelf N3000 accelerator board is utilized. The presented solution shows a high physical and performance density. We are also showing here some other possible use cases.
Hi, this is Mikko Suni from Intel. Next, let's have a look on why and how one could do acceleration in an edge server. Firstly, there are several workloads in networking that will benefit from acceleration, examples being virtual RAN, Open vSwitch, and other packet processing like IPsec. Fixed function accelerators are troublesome in an open ecosystem from the viewpoint that they only do one thing, and it may not be possible to know in advance what the platform should run in a 1 year ahead, or if it has to actually swap between different workloads on an edge deployment. FPGAs provide compromise between programmability and performance, so they place themselves between fixed function ASICs and software. In this use case, we look at accelerating virtual RAN forward error correction on an FPGA, putting a PCIe card on Open Edge server and running open programmable accelerator engine driver software framework that will help to manage and use the FPGA accelerators from the software side. Forward error correction IP is then loaded on the FPGA for the vRAN use case.
This is the case study we have here, Open Edge acceleration solution. This is the Nokia Open Edge 3U chassis solution with Intel PCIe N3000 acceleration card for this particular case. We have here the 3U chassis with 5 1U servers installed, but we could also have other possible chassis configuration options, mixing 1U and 2U servers, which are both part of the Nokia airframe portfolio. The Intel N3000 accelerator card can be installed to any of the server's PCIe slot. The target here is to compose solution for NFV, edge cloud, with maximum compute density, vRAN acceleration capability, programmability for other possible NFV applications, and the NEPS compliance. As said earlier, the 3U example solution here consists of 5 1U servers with the configuration where we have Xeon-based CPU with 24 cores and 165 watt TDP, N3000 PCIe acceleration card, 2x 25 gig OCP mezzanine to the 0 NIC, and hot swappable local storage devices.
Next, let's have a closer look at the N3000 programmable accelerator card. The main component of the card is Arria 10 FPGA with over 1 million logic elements. It has 9 GB of additional DRAM available on board. Card supports external connectivity with up to 4x 25 gigabit Ethernet or alternatively 8 times 10 gigabit Ethernet. Acceleration functions are used and managed with open source OPA driver framework in Linux. Card is connected to main CPU with PCIe Gen 3x16 interface via integrated PCI switch, which can dynamically share bus bandwidth among FPGA and Ethernet controllers. Switch also enables both inline and local-side accelerations. Networking interface towards software is provided by two integrated XL710 Ethernet controllers. These popular controllers have complete software driver support in Linux kernel and DPDK. Smaller Max 10 FPGA on board implements BMC functionality, controlling boot and maintenance of the card. It also implements security root of trust, authenticating firmware and images uploaded into the card, and implementing additional security features like anti-rollback support. There are already multiple NFV reference designs and solutions, both from Intel and partners, including vRAN FEC acceleration for 5G and LTE with front-haul Ethernet support, 5G core UPF, VPNG, segment routing, Open vSwitch offload, and IPsec. Next, let's have a look why fully virtualized base station makes sense now and what are the main requirements for it. Recently, several technology enablers have appeared that are behind increasing interest and investment towards virtual layer 1. Firstly, 5G as a new network-wide deployment allows operators to choose most appropriate implementation technology from clean table. Next, 3GPP has standardized DU-CU split, which allows distributing only the real-time sensitive parts of 5G base station and centralize the rest. In addition, O-RAN has standardized interface from baseband to radio head using Ethernet-based protocols and allowing baseband to be implemented using standard general-purpose server components. Another factor is increase in signal processing capabilities of general-purpose processors, including dual 512-bit wide vector units on each CPU core and extended instruction set that is more efficient in baseband processing. Finally, introduction of FPGA technology into server form factors allows flexible use case specific hardware accelerations for most heavy functions. Then, what are the typical requirements for virtual layer 1 edge solutions? Firstly, servers have to fit into small shelters, typically maximum 600mm deep racks with front cabling. Secondly, solutions should fit high-end Xeon SP processors for maximal baseband capacity and pooling gains. And there should be acceleration for FEC to maximize cell density and support higher carrier bandwidths. Yet, high Ethernet connectivity with 4 to 6 times 25 gigabit Ethernet per server is needed in order to support front-haul and mid-haul connectivity. And finally, there needs to be good support for accurate timing with 1588 packet timing protocol. Next, we look into details how we process and accelerate virtual layer 1 in this case study. Starting from right-hand side, end-user data arrives over F1 interface to the baseband. First, user data waits to be scheduled by air interface packet scheduler of MAC layer. After blocks of data are scheduled for transmission, they are passed to N3000 accelerator card that implements CRC calculation, low density parity coding and rate matching and returned back to software. After that, baseband software does scrambling and modulation, layer mapping and pre-coding. At this point, baseband sends downlink IQ stream in frequency domain format towards remote radio unit. FPGA may optionally implement inline compression. Above applies to category A Open RAN radio units. With category B Open RAN radio units, pre-coding state happens in radio unit itself. This pipeline is implemented with commercial off-the-shelf components, and FEC offload to FPGA is used to maximize cell density per server and allow higher carrier bandwidths beyond 20 MHz.
Here in this slide, we will show comparison of the density with alternative form factors. In the table and graphics, you can see the comparison of Open Edge and rack mount form factors in terms of solution density and relative solution density, which is taking into consideration also the utilized floor space. In the three columns, we have Open Edge 1U sled and 1U and 2U rack mount servers. We are here comparing the number of sockets, ideal config per socket, and number of configurations per chassis. In addition to utilized rack units, we also take the floor space into account, and there the Open Edge solution has half the depth compared to rack mount, which in practice doubles the density from the pure server per rack unit count. This calculation here shows clearly the benefit of Open Edge solutions density with the factor over 3 times higher than with rack mount. As a summary and conclusions of the use cases presented here in this presentation, we can say that the use of programmable FPGA acceleration increases solution capacity and flexibility. The open solution enables extremely dense solutions for vRAN video, and the NEPS compliance and small footprint enables Open Edge solutions for both indoor and outdoor deployments. On the right side, you can see examples of Nokia current indoor and outdoor cabinets. Then about the product info and where that can be found. If you are interested in getting more detailed information about the presented products, you can find those behind the link shown here. The Open Edge chassis and server are part of the Airframe Open Edge portfolio offered by Nokia, so please visit Nokia internet pages behind the link. You can also find information of the chassis and server from Open Compute Marketplace, and you can find a link here also. Behind the Intel link you can find more detailed information and specifications about the Intel N3000 acceleration card utilized in this case study. As a last topic, I would like to state the call to action. OCP Open Edge project is a sub-project under Telco project, and there is monthly project call which you are welcome to join to discuss topics related to Open Edge products. You can also find more information from the Open Edge project wiki pages, which are containing the latest specifications. Everyone interested can also join the OCP Open Edge mailing list. And now I would like to welcome everyone to visit Nokia virtual booth, where you can find more information about Nokia OCP contributions, products, and Nokia as a company. Thank you.
Hey, hi all. This is Mika Demetiev from Nokia. So thanks for listening. So looks like we don't have any questions. Okay, we have in chat. Okay, there's a question. Do you have a performance comparison between the cases using the N3000 and without the N3000? At the moment, we do not have this information at hand, but you can visit Nokia booth, and we can discuss that a bit more, what exactly you are looking for. Oh, Pasi, do you have something to add to that?
The exact number is very much a case-by-case discussion. There is a significant performance increase, particularly in layer 1 processing, by using the N3000 for the FEC acceleration. but yeah, like you said, I recommend visiting the Nokia booth and talking to the experts there, and we can help you.
Okay. Okay, we have
there's one more question in the Q&A. So the question is there other hardware needed in the implementation of this as an Open Edge vRAN? Mika, do you want to take this?
Is there other hardware needed in the implementation of this Edge vRAN? Okay, so this is I don't exactly know what this is asking.
I guess so for a vRAN implementation, the Open Edge itself with the packet 3000 performs the baseband processing function. So of course, like a full RAN solution needs also the radios themselves, and the Open Edge chassis then also has components, for example, for the front hall gateway to connect to the radios. Okay, there's another question from the chat, Mika. I'll read it out to you. So, doesn't this approach for Open RAN open Nokia's typical market for new competitors?
Okay, I think this is something I cannot comment here at the event. So this is so I'm not the correct person to comment on this.
Well,
okay,
looks like we don't have any more questions in the chat for the Q&A.
Yes. Okay. All right. So I want to thank everybody for joining this session from my part, and please do visit our booths for more information and to discuss in more detail of any topics related to these products. So thank you.
Please visit the Nokia and Intel booths for any additional information. Thank you. I think we're done.